Curvilinear coordinate systems 19. Consider a sphere of radius r0 rotating at a constant angular rate omega 0 about its z-axis so that omega is omega 0 ez hat. Part A, find an expression for the velocity vector v of points on the surface of the sphere using spherical coordinates and spherical basis vectors. Remember that v is equal to omega cross with r. Part B, perform the integration, closed surface integral dr dot v around the equator of the sphere. So this is a closed contour integral. Okay, so we're going to work on these two parts for this session. The position vector in spherical coordinates, first of all, we have to remember this position vector in spherical coordinates. We have r, the position vector r is equal to r0 sine of the polar angle theta cosine of the azimuthal angle phi in ex hat direction, and r0 sine of the polar angle theta, which takes us to the xy plane, and this time sine of the azimuthal angle phi in ey hat direction. And then we have r0 cosine of the polar angle theta in ez hat direction, which can also be written in terms of the spherical basis vectors as r0 in er hat direction. So if I follow the formal procedure here, I take a partial derivative of the position vector r with respect to r. This gives me, for the first term here, sine theta cosine phi, sine of the polar angle theta, cosine of the azimuthal angle phi in ex hat direction. And the second term will be sine of the polar angle theta, sine of the azimuthal angle phi in ey hat direction. And finally, I have cosine theta in ez hat direction. And if I look at the magnitude of this vector, this would be square root of sine square theta cosine square phi, sine square theta, sine square phi. So in sine square theta parentheses, square is cosine square plus sine square phi, that's 1. And then I have cosine square theta. So square root of sine square plus cosine square would also give me 1. Therefore, the scale factor h sub r is equal to 1. So this is the unit vector er hat. So let me rewrite it here. Er hat, the radial unit vector, is this vector. All right. Now I'm going to take a derivative with respect to the polar angle. So del r del theta. This time I'm going to get cosine theta from the first term. So r0 cosine theta cosine phi. r0 cosine of the polar angle theta cosine phi in Ex hat direction. Then from this term, I would also obtain a cosine theta. So next term is R0 cosine of the angle theta sine phi in EY hat direction. And for the last term, I'm going to get minus sine theta. So this will give me minus R0 sine theta in EZ hat direction. Now I can recognize my scale factor here, h sub theta. What is the scale factor? You can see that this is in R0 parentheses, square root of cosine square cos theta cosine square phi, cosine square theta sine square phi, which would give me cosine square theta, and this would give me sine square theta. So therefore, the square root of the when I calculate the magnitude, I'm getting 1. Therefore, the scale factor h sub theta is equal to r in this case. So this tells me that the unit vector e theta hat is equal to the same thing here, but it's divided by r0. So we don't have an r0 anymore, so that we get our unit vector. It has to have a unit magnitude. All right, so we successfully calculated the two unit vectors ER hat and E theta hat. Now, if you look at this ER hat and E theta hat, if I multiply ER hat with cosine theta and E theta hat with minus sine theta and add them up, these terms would cancel. So once again, this is multiplied with cosine theta, this is multiplied with minus sine theta, these would cancel. Multiplying this by cosine theta, I obtain cosine square, and here I obtain sine square, so that would give me EZ hat. So I also realized that EZ hat can be written in terms of ER hat and E theta hat. It's cosine theta ER hat minus sine theta E theta hat. Okay, so let's keep that in mind. Now, we were asked to calculate the velocity vector v, which is equal to omega cross r, and omega is given here as omega 0 EZ hat. So the velocity vector v is angular velocity omega cross product with position vector r. Angular velocity omega is omega 0 EZ hat. But EZ hat, I just noted that, is equal to cosine theta ER hat minus sine theta E theta hat. And I'm going to take cross product of this with the position vector R0 in ER hat direction. Since there is no E theta hat here, this would give me no contribution. The ER hat cross ER hat is equal to 0 because sine of the angle is 0. So I would have a contribution only from this term, E theta hat cross with ER hat. So I'm going to get omega 0 minus sine theta R0. So minus omega 0 R0 sine of the angle theta E theta hat cross product with ER hat. Now I have to remember what is E theta hat cross ER hat. the spherical coordinate system is right-handed. Er hat, E theta hat, E phi hat. When I form this cyclic permutations, Er hat cross with E theta hat is E phi hat. E theta hat cross with E phi hat is Er hat, and E phi hat cross with Er hat is E theta hat. So if what I'm looking for here is E theta hat cross with Er hat, E theta hat cross with Er hat. So that's going in the negative direction. Therefore, this is the negative direction. That's negative. So I would get minus E phi hat. So my answer here is velocity vector v is equal to omega 0 r0 sine of the angle theta E phi hat. This is my velocity vector I was asked to calculate. Now in part B, we perform the integration contour closed contour integral dr dot v. So I have to find what dr is, first of all, in spherical coordinates. Now dr, r is now a function of r, theta, and phi, is del r dr plus del r del theta d theta plus del r del phi d phi. And you can see that del r is the scale factor h sub r multiplied by Er hat. So I have h sub r dr Er hat plus h sub theta d theta E theta hat. And finally I have h sub phi d phi in E phi hat direction. So what was missing here is h phi. I didn't have the scale factor h phi, so let me calculate it here. What is del r del phi? Now going back to part A, the position vector is here. If I take a phi derivative, this would give me a minus sine phi, this would give me a plus cosine phi, and no contribution from this one. So del r del phi is then minus r0 sine theta sine phi in Ex hat direction. Then I have plus r0 sine theta cosine phi in Ey hat direction. And the scale factor you can see here is, if I take this into r0 sine theta parentheses, I would get square root of sine square plus cosine square, which is 1. Therefore, the scale factor h sub phi, the magnitude of this vector, is r0 sine theta. Now I can write my displacement vector dr. It is h sub r, which is 1, dr Er hat, dr Er hat. H sub theta was r. We calculated it before, so it's r d theta E theta hat. And h sub phi, we just calculated, is r sine theta. So it's r sine theta d phi E phi hat. this is my displacement vector, and this r is actually r0 here. So the contour integral I have to perform is dr is for the dot product dr with v. Now you can see that the velocity vector only has a phi component. Therefore, these two will give me no contribution. I would have omega 0 r0 square sine square theta d phi. E phi hat dot e phi hat is equal to 1. So I will have omega 0 r0 square sine square theta e phi hat dot product with e phi hat d phi. Now the closed contour integral dr dot v becomes, as we vary the angle phi between 0 and 2 pi, we're on the equator of the sphere, omega 0 r0 square sine square theta d phi, but this is evaluated at theta is equal to pi over 2, so that we are on the equator. So this gives me a 1 here. So the integral will just give me a factor of 2 pi. Therefore, my answer for this closed contour integral dr dot v is 2 pi omega 0 r0 squared. So we have the answer to part B for this closed contour integral. So what we did here was, first of all, calculate the unit vectors er hat, e theta hat, and e phi hat. So e phi hat is basically this divided by r0 sine theta. And the scale factors are basically for the magnitude of the partial derivatives, del r, del r, del r, del theta, and del r, del phi. So those scale factors are 1, r, and r0 sine theta. So this is r0. Now, velocity vector is omega cross with r. Omega was given as omega 0 ez hat, so I had to write ez hat in terms of er hat and e theta hat. And you can see that I can achieve this if I multiply er hat with cosine theta and e theta hat with minus sine theta and add them up. So these terms would cancel out and I would be left with ez hat when I do this multiplication and adding them up. So I note that omega is omega 0 cosine theta er hat minus sine theta e theta hat, and r vector is r0 er hat. So doing this cross product, er hat cross er hat is 0, e theta hat cross er hat is minus e phi hat. So this is going in the negative direction. So I would get omega 0 r0 minus sine theta, but then from this cross product I get another minus. This becomes plus omega 0 r0 sine theta e phi hat. The displacement vector dr is basically partial derivatives of r with respect to the coordinates multiplied by differential changes in the coordinates and adding them up. So for these I need to know the scale factors, which I did calculate. So substituting that here, this is the general expression for the displacement vector, differential displacement vector. When I take the cross product with v, there is only e phi hat here, so only this term counts. So I would get omega 0 r0 square sine square theta d phi, e phi hat dot e phi hat is 1. And taking this integral over the equator, theta must be equal to pi over 2 because I'm on the xy plane, and phi ranges between 0 and 2 pi, so that gives me 2 pi omega 0 r0 squared because sine squared theta is equal to 1.